right, before we deep dive more into today's presentation, I was wondering if you have ever worked with stream processing technologies before. If you did, that's great, but if you didn't, there is no need to worry, because our purpose today is to help you understand what this technology is all about. When thinking about stream processing, you can imagine it like having a magical mailbox that keeps receiving letters all day long. Instead of waiting until the end of the day to open all your letters at once, basically you can read each one as soon as it arrives and make a decision based on the message. Maybe you'd like to send a thank you note or sort your letters into different categories. Basically, any action that a person does can become an event, from clicking on the mouse to even making a payment in your favorite mobile application. Event streaming is all about retrieving data in real time from different sources, such as applications, databases, and send it to different destinations with purposes such as storage, processing, transformation, or even to generate reports based on this data. However, why should you care about it? Well, first of all, stream processing is essential to building an event-driven system. It can enable such a system to have continuous access to data and react to it in real time. Moreover, it is proven to increase the resilience of a system in comparison to batch data processing that gathers data over a large period of time and starts processing it all at once. And last but not least, it can provide the application with a better user experience. By having continuous access to data, the user can get real-time feedback, and this increases the responsiveness of that app. Let's also see that event streaming technologies can be used across a wide range of industries. They have been proven very effective in different sectors, starting with banking or gaming, cybersecurity, and even entertainment. But to build a system like this, you need to use a powerful stream processing engine. And here's where Apache Flink comes into play. As stated in their documentation, Apache Flink is a framework and a distributed processing engine that can perform stateful computations over bounded and unbounded data streams. It has been designed to run in all common cluster environments and perform computations at in-memory speed and at any scale. Now, let's take a look at what makes Flink SQL so great for us developers, because the main idea of this presentation is to prove that Flink can make our lives easier for us, for developers. Basically, Flink provides us with a set of instructions that we can apply over our data. And this can easily be compared to a basic SQL setup. You can start by querying your data, like running select statements over it. You can filter it and keep only what's relevant. You can even transform it by applying functions or mapping specific fields. You can also aggregate it and combine multiple records into one. And last but not least, a really powerful instruction that Flink SQL provides us with is join. By using this SQL statement, you are able to enrich your data and combine it with records coming in from other sources, such as databases or Kafka compacted topics. And the best part about this is the fact that it eliminates the need to write complex logic in other programming languages, such as Java or Scala or Kotlin. It's all about making stream processing as easy as writing a SQL query. However, there might be scenarios when your logic is so complex that it cannot simply be expressed by query language. Here's another point where Apache Flink proves its flexibility by enabling developers to implement their own user-defined functions. By implementing such an UDF, you can perform custom transformations, aggregations, or filtering by basically using any JVM language. Now, let's deep dive into how a Flink application actually works. For starters, on the left side of the screen, we have the client application. The main responsibility, the only responsibility, in fact, of this app is to basically trigger the Flink jobs. However, you don't need to implement an app for this. This functionality can easily be replaced by the Flink user interface or by the Flink command line interface. Then we have the job manager. You can see this component as being the entire brain of the operation. Its purpose is to orchestrate and make sure that all the tasks are running that all the jobs are running as expected. But when it comes to the heavy lifting, for that we have the task manager. The task manager is designated to do all the processing of the data. And a really nice thing about this whole system is the fact that the job manager can split the workload and add more task managers to the setup based on its needs. Therefore, Flink, this is what allows Flink to scale horizontally. The main idea is the fact that the job manager assigns the jobs to the task managers, and in turn, the task manager is responsible to provide the job manager back with a feedback. This feedback contains the status of the job execution, and it allows the job manager to have an overview on how the job concluded. All this back and forth communication has the purpose of making sure that everything is running as smooth as possible. Now, let's see what makes Flink such a great tool for real-time services. First of all, Flink is able to process your data event by event with millisecond level latency, which means that Flink is really fast at processing the data stream. Moreover, another big strength of Flink is the fact that it can ensure that your data stays correct even in cases of failures by providing exactly once and at least once state consistency. Now, in terms of scalability, Flink is good at that too. By running in a distributed cluster, it is able to divide the workload between multiple worker nodes. Moreover, in terms of fault tolerance, it also provides us with two mechanisms. The first one is checkpointing. Basically, Flink periodically takes distributed checkpoints of the application state and saves them in durable storage. Now, in case something crashes, Flink is able to pick up the job execution exactly from where it was interrupted. And the other mechanism is save points. These save points are really useful for us developers because essentially they are user-generated snapshots that can be used in cases of job updates or migrations. However, what makes them different to checkpoints is the fact that they are persisted even beyond job restarts. And last but not least, Flink is really good at managing its own resources due to the fact that it is able to request more Kubernetes resources in case the workload increases, and it is also able to release them in case they become idle. Now, let's move on to the demo part of this presentation. In order for you to understand how Flink works better, we have prepared a short demo to show you its capabilities. We have replicated and simplified the scenario that the 𝐼NG Romania business banking application is using. We have a user that is making a transaction by using his 𝐼NG card. In case that transaction has a sum larger than a predefined threshold, the user would like to receive an email notification. that transaction, that predefined threshold will be defined at the level of an object that we are going to refer to further on as a preference. However, in case the transaction sum is not larger than the predefined threshold, this will result in no email notification. From an architecture perspective, we are going to use the Kafka UI to produce an event on the input business demo topic. This event will be afterwards consumed by the Flink application, which in turn will try to match it with an existing preference by iterating over the data that we store in a Kafka compacted topic that is acting as a data cache. In case Flink finds the corresponding preference and also some other prerequisites are being fulfilled, it will produce the event on an output topic, which in turn will be consumed by the email service. The main responsibility of this email service is to make sure that, that the end notification reaches the customer. As a prerequisite for this demo, we have started some Docker containers that allow us to access the Kafka UI. Here, you can see the Kafka topics that we are going to use. The customer preference event demo topic, where we are going to have the preferences for our customers, and the input topic for Flink, and the output topic. Now, via a simple Postman request to a local service that we implemented, we are going to create a preference for an account number, which corresponds to my email address, and for the transaction sum of 100. Now, if we go on the Kafka compacted topic that is responsible with storing the preferences, you can see that the preference has been created. Moving on, we will produce an event for the same account number that we created the preference for, and for a transaction sum of 120. Basically, Kafka will help us produce this event, Flink will pick it up, and the expected outcome would be that the customer, my inbox in this scenario, will be notified in this transaction. However, sometimes it might take a bit longer for the email to arrive due to the fact that we are using our own services that are currently deployed in a test environment for the purpose of this demo. And you can see that we received a notification which states that I just made the transaction from my account and the sum of 120 RON. Basically, in this scenario, Flink makes sure that the customer is able to receive his email notification. Now, let's see how easy it is to configure the data sources that we previously saw in the Kafka UI and create configuration for them in the Flink application. One of the most important files that we have configured in our Flink project is the tables YAML file. Here, we are able to create configuration for each Kafka topic. We are able to assign an Avro schema file to it, and this will let us know how the event is going to look like, what its structure is going to be. And the most important thing is the fact that we are able to define a pattern which will let Flink know how to process the events from this topic. In this scenario, for the customer preference event demo topic, we are following the pattern of lookup table compacted topic, and we are setting a primary key called account number. Basically, this for Flink translates as having a unique list of preferences for each account in the system. Now, we can move on to the configuration that we have for the input and the output topic. We can see that for the input business event demo topic, we are following the input table pattern, which lets Flink know that it can consume the events from this Kafka topic. And last but not least, the output business event demo topic, following the output table pattern, which lets Flink know that on this topic, it should produce the outcome of the computation. Now, before we take a look at the SQL script that we executed for this demo, I would like to show you a really nice tool that Flink provides us with. And this is the Flink SQL command line interface. Via this interface, we are able to test our queries, to see how our SQL script is going to behave, and stuff like that. Now, the instructions from this CLI are also written by using query language. In this case, I'm going to do a simple select from the customer preference event demo topic. Whoops, my bad. And here you can see that the SQL query result has the actual form of a table. We have my account number and the preference that we have previously set up, together with the ingestion time. Now, if we go to Postman and create a preference for a different account, let's say replace the last digit, you can see that the result of this query will be updated in real time due to Flink's capability to perform automatic refreshes for this query. Moving on, here we have the SQL script that we executed for our demo today. Basically, it can be divided into multiple sections. First, we have the insert into statement, which tells Flink that it should produce these events on the output business event demo topic. Then, we have the select query, where we combine fields from both our input event and the preference that we have defined for them to be published onto the output topic. Then, we have the join instruction, which allows us to indeed verify that a preference exists on the Kafka compacted topic for the account number from our input event. And last but not least, we have a simple where statement that allows us to check that indeed the transaction sum from the business event was larger than the transaction sum from the preference, and also that the end time of the preference is larger than the current timestamp, because we want to make sure that, that our preference is still valid at the time of the notification. Now that you have seen all this, I would like you to take a moment and, oops, bless you, to take a moment and imagine how much time it would take to implement all of this in Java. Basically, you'd have to implement the Kafka consumer, to create the connection to the database, to do some processing logic, and also to create a Kafka producer. On the other side, for Flink, here at ING, we have a team that is dedicated to doing all the operational setup. So you, as a developer, only have to concern yourself with writing your SQL script and to have fun. Besides this, this code comparison, we also did one in terms of performance. For this, we implemented a Java application that replicates the behavior of the SQL script that we had in Flink. And we ran 2 sets of performance tests via Gatling in order to see which application has a better behavior in terms of performance. If you look at the Flink results, you can see that all of them have been processed with a response time of under 800 milliseconds. Now, on the other side, the Java application didn't perform so well. It was able to process all of the requests, but we were able to see a lot of delays in terms of the response time. Some key observations that we extracted were the fact that both applications had a 100% success rate, but in terms of response time, the Flink app had significantly lower values for response time. From consistency point of view, the Flink app proved to be more reliable by having a lower standard deviation. And last but not least, the Flink application was able to process more requests per second than the one that we implemented in Java. Now that you have seen these numbers from our test application, we would also like to show you some real-time statistics that we have extracted from our own production data. Our client applications are triggering around 500,000 requests daily that they intend to result in notifications. However, due to the fact that not all of them are eligible, Flink is filtering out around half of them daily, and all for the 4 use cases that my colleague Alin presented at the beginning of the presentation. Moreover, we have also prepared a video that was recorded from the Romania Business Banking app, a video that will allow you to see how this application benefits from using Flink SQL. Here, you can see that the customer is filling the details for his transaction. Next, he's going to validate them, to confirm his payment, to authorize it, and if you pay close attention to the upper part of the video, you will see shortly 2 push notifications that are going to be received on this application. The first one, this will be for the commission of the payment, and the second one for the actual payment that was debited from the user's account. All right, thank you for your attention. I would like to pass the mic to my colleague Alin, who is going to present you with the conclusions for today's presentation.
Right, thank you, Andrea. So, in conclusion, you've seen how at ING we have lots of events that we need to process in a stream to fulfill some business needs. You saw how we used Flink for that. You saw a demo. And then we also showed you some performance results for this solution. And also you can see that Java is not always the right tool for the right job. Is not always the right tool, so you have to use the right tool for the right job. If Flink makes more sense in your use cases, maybe it's better to use that in the future. So that's all we have for you today. Thank you, and follow us on social media, of course. And now, questions. If you have some questions, we have some goodies. Yes, please.
I have a question in regards How do you handle this granting of permissions to users, or do you handle this with Apache Flink?
No, that's a different system that handles that. Actually, multiple systems. We have, as I said earlier, one PAM, and there's also another system, bigger area of one gate, which handles all the authorization and the authentication mechanisms. You're welcome. Yes, please.
Nice presentation, by the way. Congrats. You were mentioning earlier something about a parallel between a very complex query versus where Flink comes to the rescue. What would such a very complex query look like?
Well, maybe you'd like to have custom transformations. Maybe you'd like to compare multiple fields, or I don't know, iterate in more depth through your data. And on the Apache Flink documentation, you will be able to see different examples on how the user-defined functions can be used.
The beauty of this system is also coming from the fact that we, instead of implementing custom logic in Java for every use case that comes to us to be implemented, we have a simple system that we do not change other than adding some new configuration and a new SQL script. And this is all, a new use case can be onboarded at runtime. We don't have to redeploy everything to implement new code and then redeploy. We just create new configuration that we update dynamically at runtime. Yes, yes. So the comparison is between Java code and Flink queries. Yeah?
Still on the topic of complexity and using Flink. In classic relational databases, you could have more complex scenarios where you would have to use transactions or afterwards use stored procedures, user-defined functions, and so on. Does Flink support all that, or does it have any failover mechanisms for this as well?
We didn't get in depth with this in our scenarios, but maybe it will be food for thought for the next presentation.
Of course, you can, if you have some complex logic that cannot be expressed in Flink SQL, there is also something called user-defined functions, just like you said earlier, that you can implement for Flink to then use into the system. So yes, if you really have to use some custom logic and custom code, then you can also integrate that. Yeah.
You've shown us the SQL, so it's very flexible because you have this, capability via the script. But how easy it is to debug and troubleshoot, have issues? Can you debug it?
Yes, this is more of a responsibility of our ops team, but they provide us with support, with logging mechanisms that allow us to see where errors might have been encountered and stuff like that.
And one more question. You mentioned about exactly once processing. So where exactly does the, the duplication or, notification mechanism sit?
Sometimes that duplication might come, let's say, from not creating checkpoints in an enough recurrent way. So in case the job restarts and the previously executed checkpoint was not completed or not stored properly, because there might be cases of errors, especially in the testing and in the development phase. Some of those events might be processed again, but that can be avoided with setting checkpoints that happen often enough in order to reduce this risk.
Yeah.
So, what about, you mentioned Java versus this way of, scripting the business logic, but we also do, advanced configuration regarding to, how the consumer, uh, particular attributes about the conversation with the producer, like timeout, stuff like this. So, where would that be, defined?
As far as I know, it's in the configuration of Flink. Just like you can configure the Kafka producers and consumers in a usual application in Java, you have such configuration that you can use also for Flink. Okay, one more.
How does it scale? Let's say you have the Black Friday when the number of payments increases a lot. How is it compared to Kafka? And how does the cost compare to using the Kafka solution in case you have also increased?
Well, first of all, it also uses Kafka. So Flink is not replacing Kafka. It's actually relying a lot on Kafka, indeed. But in terms of scaling, maybe.
Yeah, in terms of scaling, this can be done automatically by Flink. So it will be able to determine on its own if the workload is too much, and it can add additional worker nodes to the whole setup to execute the jobs and do the processing logic.
So it will behave basically just like any other application deployed in Kubernetes. When it needs more resources, it will ask for them and will receive it from the cluster if configured properly. Yeah.
What about in cases of like DR, for example? How would you go back to a state in sync? When it was processing messages, let's say, and the whole server shut down. How does it happen?
Well, let's take it step by step. For DR, if I remember correctly, you have to make to switch your application to a different data center, because what we currently have, we have Flink running only on one data center. Usually microservices are deployed in multiple data centers and they all work in active solution. In this case for Flink it's not possible, so they work only on one data center. So before a DR exercise, for example, we are being asked to move all the workloads to the different data centers so the other one can be shut down. But in terms of going back to the state previously, we have, like Andrea said earlier, checkpoints, save points. So by design, Flink has checkpoints that you can configure to be as often as you want, so that either you have often checkpoints, but then, I don't know, maybe more resources will be used for that, or to save points that are not that often, but then good enough for your use case. It depends on how tolerant you are to such a failure. Okay, oh, one more. Do we still have, let me see if we still have time, but yeah, last question, and I think we can, yeah. Yes.
And how did you measure the response times, the processing times, since reading from a Kafka topic is the same?
Yes, we are basically doing the comparison based on how fast the event was ingested on the output topic. So we do a difference between the time when the event was produced and how fast it reached the output topic.
We also have different performance tests based on, for Kafka systems, where we measure the time that it takes for an event to be processed, starting from the ingestion from the topic, then until the point where the event has gone out to a different output topic. So we measure how long it takes for that event to go through all the systems inside our applications, from the start of the ingestion of the event to the output topic. Okay, that's all we have for today. Thank you very much for your presence and for questions. Thank you.